In today's video, we will look at the frictional force. Friction is a force that occurs when two surfaces are in contact and one of them tries to move relative to the other. The amount of friction depends on the surfaces in contact. The friction between two wood surfaces is different from the friction between a wood surface and a metal surface. Friction also depends on the normal forces between the surfaces. That is, it depends on how tightly the surfaces are pressed together. We will look at two types of friction: static friction and kinetic friction. There is a third, called rolling friction, that we will only mention in passing. One thing to note is that usually what confuses students is the direction of friction. The frictional force is modeled by the equation F equals mu n. Notice that this is not a vector equation. It only relates the magnitudes of the frictional force and the normal force. At the moment, this is not yet a correct equation because I haven't yet specified is it static, is it kinetic, and so on. Mu is called the coefficient of friction. Since both the frictional force and the normal force are forces measured in newtons, we can see that mu, which would be the frictional force divided by the normal force, will be a dimensionless number, right? A pure number without units. That's why it's just called the coefficient. So mu is the coefficient of friction. If we are dealing with static friction, we write mu sub s. And if we're dealing with kinetic friction, we write mu sub k. Mu depends on the surfaces which are in contact. So the mu for a pair of wood surfaces in contact would be different from the mu for a wood surface and a steel surface in contact, or a pair of steel surfaces in contact, and so on. As we stated before, the frictional force also depends on the normal force. And so if the normal force and mu stay constant, then the amount of area in contact between the two surfaces does not matter. So it does not matter if it is a large area in contact or a small area. All that matters is how tightly the two surfaces are pressed together, which is given by the normal force. Static friction occurs when you try to move an object which is at rest. It's a little unusual because it's not a fixed force, it's a force that adjusts to how much force is applied. This will be clearer with an example. Let's try and move a book. So we have a book resting on a table. The friction is between the surface of the book and the surface of the table. And let's say I apply a force of 4 newtons, which I depict like this. If the book doesn't slide, then there must be an opposing force stopping me. In this case, that is the static frictional force. So it has the same magnitude, points in the opposite direction. Now, if I'm drawing just a free body diagram, I'll move this arrow up here, but for the moment I want to emphasize that it is taking place at this surface. So, static friction opposes the attempted motion. Notice, there isn't actually any actual motion between the book and the table. The book hasn't moved. And it hasn't moved because static friction has opposed this attempted motion. As stated before, here is the free body diagram. The applied force and the frictional force. As usual, the arrows starting from the dot representing the book. There isn't any actual motion, so the velocity is 0. Now, the frictional force isn't fixed at 4 newtons in this case, Let's say I increase the applied force to 9 newtons. But the book still doesn't move. What has happened? The static frictional force has also increased to 9 newtons. This is what I meant by the static frictional force being an adjustable force. So, does the static frictional force just keep on increasing without limit? No. If it always increased, then there would never be anything sliding or moving. There is some maximum value that the static frictional force can increase up to, and it can't go any further. So the equation we write is Fs max is equal to mu s times n. Now let's note a few different things. 1. The static frictional force is adjustable. It can take any value from 0 in magnitude to the maximum magnitude of mu s times n. 2, well, we just said it depends on the normal force, so there's something missing from this diagram. I've forgotten to draw the weight of the book, which would be acting downward, and the normal force, which would be acting upward. However, the normal force, remember, isn't always equal to just the weight of the book. It depends upon the forces pushing the surfaces together. If I were to apply a force downward besides the weight of the book, for example, supposing I were to put my hand here and press downward, then the forces pushing down have increased, and so the normal force increases in proportion. As the normal force increases, the maximum static frictional force can also change. So, the maximum static frictional force depends on mu s times n. The actual static frictional force could be anything from 0 to mu s times n. As a reminder of this, we sometimes write the equation as Fs is less than or equal to mu s times n. This reminds us that the static frictional force is adjustable. It has an upper limit, which is given by mu s times n, but its actual value can be anything less than that. Also notice that the direction of the static frictional force and the direction of the normal force are not the same. Alright? They are in fact perpendicular to each other. This equation only relates the magnitudes. If we increase the applied force beyond the maximum value, what happens? Well, then the acceleration is no longer 0. And once the acceleration is no longer 0, the object starts to move. And once it moves, we have sliding between the two surfaces. And so we are now dealing with kinetic friction. Kinetic friction is always equal to mu k times n. It's not an adjustable force like static friction. Now, usually the value for mu k is less than mu s. And so, it may be hard to overcome static friction and start an object moving, but once you do, the amount of force required to keep it moving will be less, because we have shifted from the greater static friction to the easier kinetic friction. So, if the applied force is then reduced to become equal to the kinetic frictional force, then the net force on the object is 0, and it will move with a constant velocity. If the applied force is greater than the kinetic frictional force, then there's a net force, and it will accelerate. So, what about what I was saying earlier about the direction of friction? When we are dealing with kinetic friction, we have two surfaces where one is sliding past the other. The direction of kinetic friction will act to oppose this motion. So, for example, supposing we have a table and a box, and the box is sliding this way, and there is some friction between the box and the table, well then there will be forces of kinetic friction. Now, why did I say forces? Like everything else, friction is generated in action-reaction pairs. So, the force of the table on the box will be this way in opposition to the motion of the box. However, the box will also exert a frictional force on the table, and that would be in the opposite direction. That is, the frictional force by the box on the table would be acting on the table in this direction. Why is that? Well, from the box's perspective, the table is sliding this way, and so to oppose it, the box will exert a frictional force in the opposite direction. If that seems confusing, just remember that, as I said earlier, friction comes in action-reaction pairs, just like every other force. So, if the force by the table on the box is this way, then the force by the box on the table will be this way. And remember, they belong in different free body diagrams. The friction by the table on the box will be in the box's free body diagram, whereas the friction by the box on the table will be in the table's free body diagram. Static friction, finding the direction of that, is a little bit trickier. Here we have two surfaces that are trying to slide past each other, and static friction opposes this attempted sliding. Strangely enough, though, this may, as a result, actually cause motion. Here is an important everyday example. Let's look at what happens when we try to walk. When we push against the ground, we push down and backward. So there is a component of the force exerted by us on the ground. This is the normal force that we exert on the ground. And in response, the force of the ground exerted on us. So this is a normal force, and this is also a normal force. Remember, they belong in different free body diagrams. This is in the ground's free body diagram. This is in our free body diagram. And then our shoe, in moving backward, attempts to slide against the ground in the backward direction. And so the ground reacts to that attempted sliding by creating a frictional force acting on us in the forward direction. It is this frictional force that actually pushes us forward and allows us to walk. So, if there was no static friction, then we would not be able to walk. After all, static friction is what gives us grip, right? It allows our shoes to grip the ground, it allows tires to grip the road, and so on. So let us look at another example. Here we have two books, one on top of another, in a pile on a table. I apply a force on the lower book. Let me draw its free body diagram. I'm going to ignore the vertical forces since they cancel out, and I'm just going to focus on the horizontal forces. There is the applied force, and there are two frictional forces. There is the friction between the table and the lower book, and there is the friction between the upper book and the lower book. And they both oppose this attempted motion, and so they point in the opposite direction to the applied force. But let's say that I succeed in moving this pile of books across the table. Then the friction by the table on the lower book will be kinetic friction, but the friction of the upper book on the lower book would be static friction, assuming that the two books move together. But what about the upper book? If it is moving together with the lower book, what force is causing it to move? I mean, as long as I don't push too hard, the two books will accelerate together as a single pile. So what force is causing the acceleration of the upper book? It has to be friction. Like all other forces, friction comes in pairs. So, if the upper book is exerting friction on the lower book must be exerting friction on the upper book. And again, of the same kind. If the force that the upper book exerts on the lower book is static friction, then the force that the lower book exerts on the upper book must also be static friction, of an equal magnitude but opposite in direction. So, the free body diagram for the lower book is here, and this is the free body diagram for the upper book, again looking only at horizontal forces. So, in opposition to this frictional force, there is a frictional force over here on the upper book by the lower book. If we know all the coefficients of friction, that is the friction between the two books and the friction between the table and the book, then we can find the maximum force that I can apply to the lower book so that the books move together without slipping or sliding. Let us say that we are given that the weights of both the lower and the upper book are the same, 5 newtons. Further, that the coefficient of friction, kinetic friction, between the table and the lower book is 0.1, and the coefficient of static friction between the two books is 0.4. Now, to determine how much we can push the lower book so that they move together as a pile, we focus first on the upper book, because that is the one that is being moved purely by friction. I have completed the free body diagram, adding the weight of the upper book and the normal force by the lower book on the upper book. Since these two forces balance each other, and we know that the weight is 5 newtons, then the normal force must also be 5 newtons. In that case, we can calculate the maximum static frictional force, which will be μs times n. Plugging in the numbers, we see that this works out to a maximum static frictional force by the lower book on the upper book of 2 newtons. So, how do we go from this to the applied force? Now let us focus on the lower book and draw a more detailed free body diagram. Now, due to lack of space, I haven't labeled things clearly, but let us explain. So we have the applied force, we have the static frictional force, right, pointing to the right over here, which is due to the upper book on the lower book. We have the kinetic frictional force, which is due to the table on the lower book. We have the weight of the book, and we have two normal forces. This is the normal force of the table on the lower book, and this is the normal force of the upper book on the lower book. Remember, whenever you have two surfaces in contact, you have normal forces. So since the lower book had two different surfaces, its upper surface and its lower surface in contact, there were two normal forces, and also in this case two frictional forces. All right, where can we go with this? Well, we know the value of Fs max, that's 2 newtons. What about Fk? Well, Fk is given by mu k times n. But which n? Which surfaces are we talking about? This kinetic frictional force is between the table and the lower book. So the normal force that we want is also between the table and the lower book. In other words, it's this one. But this normal force has to balance out both of these, the weight of the lower book and the normal force due to the upper book. But we know that this normal force corresponds to the weight of the upper box, and this has the same magnitude of 5 newtons, and so the total here is going to be 10 newtons. So the normal force of the table on the lower book is 10 newtons. Plugging in the numbers, we get a kinetic frictional force by the table on the lower book of 1 newton. So now we can see that the maximum static frictional force is 2 newtons, the kinetic frictional force is 1 newton, and so the maximum applied force that we can apply and have the two books move together would be 2 plus 1, 3 newtons. If we apply anything more than that, then there will be sliding between the two books. Run through the steps again and get used to the procedure. Let's move on to another example. Take a moment to read the problem. We now proceed with solving. The first thing we need to determine is, does this block have static friction with the lower block, or does it have kinetic friction? In other words, if the two blocks move together, then it's static friction. If this block slides on top of the lower block, then there's kinetic friction. How do we determine which one we're dealing with? After all, we're given both the coefficients of friction. Well, we determine the maximum force of static friction and see if the applied force exceeds that. We know that the maximum force of static friction will be the coefficient, 0.6, times the normal force. And in this case, the normal force is simply balancing the weight of M2. Here is the free body diagram for the upper block M2. The normal force is balancing the weight M2G. If we take G to be 10 meters per second squared, then M2G would be 100 newtons, and so the normal force would be 100 newtons. That times the coefficient of static friction, which is 0.6, would give us 60 newtons. However, the horizontal force F that is applied is 100 newtons, and so it exceeds 60 newtons, and static friction will not be able to reach 100 newtons. So we overcome static friction and move on to kinetic friction. So this block, M2, starts to slide on top of M1. Now that we know that it is kinetic friction, we go ahead and put a little subscript K on the frictional force. Okay, so how much is the frictional force? Since we're dealing with kinetic friction, we look at the normal force, which we know is 100 newtons, and the kinetic friction coefficient, which is 0.4. So we see that the kinetic frictional force will be 0.4 times 100, 40 newtons. The forces in the y direction balance and cancel each other out. What about the forces in the horizontal direction? Well, this is 100 newtons, this is 40 newtons, the net force is 60 newtons to the left, and so from that we can calculate the acceleration. Using F net equals m2a, we rearrange and solve for a. F net we know is 60 newtons from 100 minus 40, and m2 we know is 10 kilograms, and so the acceleration is 6 meters per second squared for block m2. We now focus on m1, the slab beneath. This is the free body diagram for the slab. There is the weight of the slab acting downward. There is the normal force from the block m2 on the slab m1, and then there's a normal force from the ice on the slab m1. There is also the reaction to the kinetic friction that we saw earlier. And like every reaction pair, this points in the opposite direction. That is, it points to the left. It has the same magnitude of 40 newtons and points to the left. This is the only horizontal force, in fact, acting on m1, because there is no friction between the ice or the frictionless floor and the slab m1. Again, the vertical forces cancel out, and so we only need focus on the horizontal force. We know that that is 40 newtons, and that the mass of m1 is 40 kilograms. And so solving for the acceleration, we get 1 meter per second squared for the acceleration of the slab. Interestingly, what we find is both the block and the slab move and accelerate to the left. Basically, what is happening is this force accelerates the block to the left, and the kinetic friction between the block and the slab drags along the slab. However, the kinetic frictional force is not strong enough, and so the slab is dragged along at a slower rate compared to the block. Eventually, this block will accelerate past and off the slab. Here is one final problem. Take a moment to read through the problem. We now start to solve the problem. We start, as usual, by drawing a free body diagram. Here is the free body diagram for this little block, little m. We have the weight of the block, which is acting downward. We have the applied force F, which is acting to the right. We have the normal force from the big block on the little block. Notice that this normal force pairs up with the applied force F. That is because the surfaces in contact are vertical, and so the normal force must be perpendicular to those surfaces. In that case, it's pointing like this. There will of course also be a normal force by the little block on the big block, but that belongs in the big block's free body diagram. What else do we have? Well, what is stopping the little block from slipping downward? It must be frictional force. How do I know it's static friction? Well, if it was kinetic friction, that would mean there is slipping between the two blocks. But we're trying to prevent that, and so it must be static friction. Similarly, when we talk about the friction between the tires on our car and the road, if the tires are working properly and gripping the road, then it must be static friction. Even if your car is moving, it's static friction that prevents the tires from slipping on the road. Now, in fact, the diagram that I've drawn here, while technically correct, is actually somewhat misleading, because it seems to imply that this force is balanced out by the normal force. In fact, however, since there is no friction over here, this entire assembly is going to be moving and accelerating to the right, which means that the net force is to the right, which means this arrow should be a lot larger than this arrow. We'll remind ourselves of this by putting an acceleration arrow pointing to the right. What about the free body diagram for the larger block? This is the free body diagram for the larger block. We have the weight of the block, we have the normal force from the table to the block, and we have the normal force from the little block to the block. This normal force and this normal force are action-reaction pairs. Also, to keep as a useful reminder, remember that we are trying to have these two blocks move together, so their accelerations must be the same. To avoid confusion, let me label this normal force as NT for table on the block, and these normal forces as NB since they're between the blocks. Now to solve the actual problem. To prevent the smaller block from slipping with respect to the larger block, we need mg to be balanced out by the static frictional force. Since we want the minimum magnitude of the horizontal force required to keep the block from slipping, this must be right at the limit, Fs max. So we have Fs max is equal to little m times g. Taking g to be 10 meters per second squared, and since we have little m is 16 kilograms, that tells us that this is 160 newtons, so Fs max must be 160 newtons. Using Fs max equals μs times nb, since that is the normal force for the surfaces in contact, we have Fs max, which is 160 newtons, equals 0.38 times nb. Solving, we get nb will be 160 newtons divided by 0.38, which gives us 421 newtons. So now we know that both these nb's have a magnitude of 421 newtons. However, we want to find this force F. How do we get there? Well, in what equation does F appear? We see that F appears in the F net x equation for the little block, which we can write as F minus NB equals little m times A. We know what NB is, that's 421 newtons. But what about A? We don't know that yet. So we have to first determine A in order to determine F. Luckily, A appears in one other place, that is here. So let us write the F net equation for the big block. This F net equation is quite simple. We just have NB is equal to big M times A. Knowing that NB is 421 newtons and that big M is 88 kilograms, we find that little a is 4.78 meters per second squared. We can now use this value in this equation. Rearranging, we have F is equal to NB plus little m times A. NB is 421 newtons, little m is 16 kilograms, and little a is 4.78 meters per second squared. Plugging in the numbers, we get that F is equal to 497.6 newtons. Go through the problem again and understand the procedure that we used to solve it. As usual, we started by drawing the free body diagrams and writing the F net equations. We noticed that the frictional force had to be balanced by the little block's weight, mg, and worked our way through there to figure out the required normal force, and from the normal force to the acceleration, and from the acceleration to the applied force F. That's all for this video. I'll see you in the next.